Hello, everyone. My name is Daniely, as he said. I'm a researcher in Center of Energy and Petroleum Studies at the Universidade of Campinas. And today we'll present, I am pleasure to present my work titled Body Fraction Measurement in Multiphase Flow, Sensor Calibration and Performance. So this is just the outline of my presentation. Here we begin with motivation and sensor principles. After that, the sensor, I will present the sensor and electronic circuit. After then, I will present the experimental test and results, and finally conclusions. So the body fraction is the key parameter that we just seen. This refers to a proportion of the volume occupied by gas in relation to total volume. It's a very important variable for the energy and petroleum industry. And the accuracy of this measurement is crucial to safety and the optimization process. Here we have one video from this example of a flow. This is the sludge flow, where you have a large gas bubble and the liquid mass phase. And here we have one example of this body fraction measurement, where the peaks represent the passage of gas bubble, where the body fraction is high, and the values represent the liquid passage of liquid mass, where the body fraction is low. Here we have two examples of the electrodes of body fraction, to rise and water mesh. So this is very complex flow to study, and we need for high quality experimental data to validate and improve theoretical models, because this is important to advance of developing new measurements of the sensor with more accuracy, faster and more reliable. So here is our sensor. The fundamental principle is just measure the difference in electrical conductivity between the phases of flow. In this case, the water is conductive, the gas is non-conductive phase. So here you have the electrode. We have 4 electrodes here, where one line is the transmitter and other is the receiver. We apply an oscillating signal in transmitter and measure in the receiver. Here we have our electrical module with a resistor and capacitor. This is our simplified circuit, electronic circuit, where we have the input signal, it's an oscillation, as I said, in 3,200 hertz, two multiplexers, where it's switching between the sensors, in this case S1 to S5, controlled by these 2 digital input, improved by embedded system. After that, we have amplifier circuit. Okay, move on to our first test. It's a calibration curve. To perform, the objective is to perform a statistical test to establish the sensor calibration curve. This is our setup. It's closed and controlled. The methodology consists in adding control volumes of water, where increases added to a experimental system, each 50 ml of water, and measure the sensor response. Here you have the results, where the liquid hides in vertical and the horizontal have a phase fraction or conductive fraction. Each blue dot is a sample of our sensor. We have a good relationship between the linearity adjusted and the experimental results. It's a very good results because see the accuracy of measurement of liquid heights. Okay, move on to our second test. It's a dynamic test. Here we has interesting other parameter, the dynamic response of the conductive sensor to a step like input at the liquid air interface. Here we put the sensor in the vertically and apply to act as a step input format by liquid interface. So we have recorded this liquid interface by a high-speed camera at 1800 frames per second. And the synchronization between the image and the sensor response is obtained by a trigger camera. Here is just a photo about the imaging process, where we can obtain the interface of water. Here is in blue line is the image input, and this response of sensor is red. So we have a system of a single input and single output. So we can do some analysis with just a single input and single output model. The first two analysis is obtain the FRF, frequency response function. This is the blue lines. It's H1 calculated for this equation. The direction line is coherence that measure the linearity between input and output system. Here is the phase of our system. We can see the phase is linear when we have a high coherence. This is very good results because indicating that its response is a simple time delay without distortion in this frequency range where we have interesting. Okay, this is our other analysis possible to a dynamic test, where it's the response of sensor only. And we can measure the 10% of maximum amplitude and 90% of maximum amplitude, and calculated this delay time, and obtain the rise time and the rise frequency by this formula. You can see the rise time is 0.198 to 0.571 seconds, and the rise frequency is 1.7 hertz and 4.7 hertz. So this is the last test. This is just to evaluate the efficiency of the sensor to measure conductive phases, water, under three phases conditions. In this case, oil, water, and gas. So the conductive phase is just water. For that, we tested sequentially and control agent oil and water into the pipe. This is the same setup that we used in the first test. So the procedure consists in added the initially oil, increase the of water with a constant oil volume, increase the oil with a constant water volume, and finally increase of water. So we record the sensor response in this our step. It is better to see what I said in procedure. In the first moment, we increase the water with constant oil volume. We can see that it's very good. The trend of a theoretical and the experimental is almost equal. And here we increase oil with a constant volume of water volume. This constant line, because the sensor just measure the conductive phase, and after that we increase the water with a constant volume. We can see some discrepancy in this measurement, mainly in this first one stage. This is attributed because the menisci at the interface between the fluids, because here we have more than one. In this case, water water oil and oil gas. So here was one example of a real example of a real application in our sensor in our laboratory, where here we have a body fraction signal separated by each bubble, and we can obtain many parameters of this flows, like velocity, slug frequency, length, and the others. For conclusions, the conductive sensor demonstrated a linear and accurate response in a liquid highs measurements. The dynamic characterization provided the sensor has a linear phase. And the three-phase conditional, the sensor response is selecting to only the conductive phase as I expect. So I would like to say thank you for all my colleagues in my laboratory, Petro and the Alpha, and the Petronas for the funding of my research. Thank you very much.